Hello Internet, welcome to another tutorial in Digital Electronics series. We'll study full subtractor today. Full subtractor is a little trickier than the previous combinational circuits we've studied. The half adder, the full adder and the half subtractor. In full subtractor, we have a task of subtracting 3 bits. Now it may sound a little weird that how can we subtract 3 bits, but in real life scenarios where bytes are being subtracted from each other, we need to take into account the borrow from the adjacent position while subtracting 2 bits, and that particular case is dealt with full subtractor. So we have 2 bits A and B which are needed to be subtracted, and this borrow in is the borrow from the adjacent position. So we need to take into account the borrow from the adjacent position, because when we are subtracting bits in a bigger number, for example in a nibble or a byte. Now all in all, this circuit will be a combinational circuit with 3 inputs, A, B and borrow in, and it will have 2 outputs, the difference and the borrow out. Now firstly, I'll explain how the subtraction occurs and how this truth table is populated, because most of the times students get confused in populating this truth table. And once this truth table is filled up properly, then we can simply put in the values of difference and borrow out in the K-maps to find their expressions, and then we can find out what all is there inside the full subtractor. So we'll draw the logic diagram afterwards we've solved the K-maps. Now how do we get to this output in full subtractor is what we are going to discuss now. Now a simple method is to perform subtraction between the first 2 bits, then perform the subtraction of the result that we get here with the borrow in, and whatever the result and the borrow output is there, we write it as difference and B out. So in other words, first of all, I'll explain this with an example. If let us subtract 0 from 0, we'll get a 0 here as difference. Now what about this? The result is 0. We need to now subtract this 0 from this result. So what happens when we do that? We get a difference of 0 which we write here, and we do not need to take a carry here, or we need not take a borrow here at this position. So we say the borrow is also 0. Similarly, when we do the next thing, when we subtract a 0 from a 0, we get a 0 as difference. But now if I subtract 1 from a 0, I'll need to take a carry, I'll need to take a borrow, and this will make it as 2, and 2 minus 1 is 1. So the difference will also be 1, and we have also taken up a borrow here. So a borrow is also 1. I hope this is clear now. And similarly, you can go on and find the rest of the things. So when we go 0, when we subtract 1 from a 0, we get a borrow here, and we get a difference of also 1, because when we subtract 1 from a 0, it borrows 1 and makes itself 2, and 2 minus 1 is 1, and then the result is 1. And if we subtract a 0 from a 1, we get a difference of 1, and of course the borrow is required in the previous stage, so the borrow is also 1. Similarly, in the next case, when we subtract a 1 from a 0, we need to take a borrow, and the result difference is 1. When we subtract 1 from a 1, the difference is 0, final difference is 0, and the borrow is of course 1. And let's see, when we subtract a 0 from 1, we get a difference of 1, and when we subtract a 0 from 1, we do not need to take a carry or a borrow, and we've got a borrow 0 at the output. And similarly, you can fill up the rest of the truth table. I've filled up the complete truth table. Now for difference, we have for 0 0 0 the difference is 0. For 0 0 0 the difference is 0 here. So I'll quickly fill up the table. So the K map is filled up like this. So from this table we fill up the K map positions, and all the diagonal entries that we get like this, they make up the minimization as A XOR B XOR B in, or in an expanded form it looks something like this. It is A bar B in plus A bar B in bar plus A B bar B in bar plus A B in. Right? So that becomes the expression for difference. And for the expression of borrow out, we need to fill in the ones first. So I'll fill up the ones here. If you check, we have a 0 0 1 position, which is 0 0 1, so the borrow is there. So I'll put in a 1 here, and so on and so forth. So you can fill it up. 1 1 1 also gives us a borrow, so 1 1 1 is a 1 here. And in order to get a minimized equation, when we solve this K map for borrow out, we'll get 3 product terms. Let us solve them. The first one will be A bar B. The second one will be A bar B in. And the third one will be B in. Alright, so what we got here is the expression for difference is A XOR B in, and the expression for borrow out is this one. And if we go on to draw its logic circuit, we'll take 3 inputs, A, B and B in. So we'll take A and B first, we'll XOR it, then we'll take B in and we'll further XOR it to get the difference, and then we'll get A bar, we'll AND it with B, we'll take A bar again, this time we'll AND it with B bar, B in, and then finally we take B and B in, and the output of these three AND gates is given to an OR gate to form borrow out. So difference is this and borrow out is this. So we need 2 XOR gates, then we need 3 AND gates, we need an inverter, and we need a 3 input OR gate. So that is how the logic circuit of full subtractor is realized. Recapitulating the concepts here, full subtractor is a device which is used to subtract 2 bits, taking into account the borrow in from the adjacent position, and it gives us a difference and a borrow out. The truth table is calculated by subtracting the B from the A first, and then the B in is subtracted from the results, and then the difference and borrow out are accounted for in the columns for output. Then truth tables will help us fill up the K maps, and from K maps we'll derive the expressions for difference and borrow out. The expressions for difference and borrow out will help us make the full subtractor circuit. And I hope this quick tutorial on full subtractor was of help. If you liked the video, give it a thumbs up, consider subscribing to the channel. I'll see you in the next one. Good day.